We have a duo of talks together now. The first is Chris Farmer from the University of Oxford, and then he'll be followed seamlessly by Poul Hjorth from Technical University of Denmark. So, Chris, over to you.
Well, good afternoon, ladies and gentlemen. Well, I'd like to start by thanking the organisers for inviting me to give you a talk this afternoon. When I received my invitation, which I think came directly from John Ockenden representing the committee, he asked me to talk about my experiences in the oil industry. So I should say that I'm recently, as it were, took early retirement from the oil industry and became an academic at quite an elderly age. I've done my career in reverse. And before I worked in the oil industry, I worked in the nuclear industry. And when I came to prepare my talk, I thought that I would abstract from my experiences and try and give you some flavour of how mathematics is used in a workflow in large engineering companies. But I do believe my remarks have a wider significance. I should just say I've been funded by many organisations over the years and collaborated with many people, so it would be invidious to make a list. But I just say Jeff Dewin and Ozzy Rithis are current collaborators, and I'm going to say a little bit about our work on dynamic pricing in the middle of this talk. So my main idea is to take 4 themes, and I'm lucky that I was encouraged to write a paper. The reference is here, so that's part of the proceedings of this meeting, and some of them are already online. I noticed my paper has been reprinted in the booklet that was left on the chairs. I haven't got time in my 15 minutes to summarise the paper, so I'll direct you to that for the references and for more detail. And in fact, I've got more themes in the paper than here, but that's what I'm going to do. I'm going to say a little bit at the end about collaboration, and that will lead into Poul Hjorth's talk, who's going to concentrate on the collaborative aspect. So let me start by saying something about the problems that are faced by oil companies, which are enormous businesses, take huge risks, financial risks, as well as physical risks. And so what happens is that there's a so this is it's a sort of typical workflow. So there's speculation by geologists that some particular geographic area deep down below the seabed might contain some oil. And they've got a reasonable idea about the global structure of the Earth, so they can make a good guess as to where oil might be found. And then they start off by doing a seismic survey, which involves sending ships, special seismic boats, backwards and forwards over the sea, and taking a lot of information, huge amounts of data that would swamp the hard disk of a computer within seconds. And the reservoirs these days are often several kilometres below the seabed, where the pressures are very high, the temperatures are very high. Now here I've said the data is sparse. Now what I mean by that, not that there's not much data, there are thousands of gigabytes of data, but it's sparse in the sense that it's insufficient. Indeed, even if there was an infinite number of data, an infinite amount of data, it still wouldn't be enough for us to know what the system is that we're dealing with. And furthermore, this is a schematic, the geological structures that you find are enormously complicated because they've been there for millions of years, and the Earth's sort of dynamic processes has really scrambled the rocks up. And what the oil company is interested in is not data, not science, not forecasts. They're interested in making very expensive, risky decisions, and they want to make the best decisions. And so really my talk could be prefaced by asking you the question, what constitutes a good decision? How do you decide that a decision was a good one? And I'll try and remember to make a remark about that at the end. So the kind of questions that the oil company asks are, how much hydrocarbon, oil, gas, is actually in the rocks? And they don't know that very well. You might only know it to within 50%. You've got to make a decision. Is there enough oil there to make it economically viable to develop the field? And over a period of time, you might be drilling hundreds of wells into the field, each one costing you millions of dollars to drill. And you want to know how much oil are you likely to recover from this oil field, and that is, can you pay for all the upfront costs that you put in? It costs billions of dollars just to set things up before you make any money. And you have to make decisions like how big should the platform be before you know how much oil is there. And just to say that very often these fields can be developed on the basis of a seismic survey in one test well, and they make an investment decision of billions of dollars on the basis of that. But because the science and the maths is good, they don't often get a dry hole these days. So let me say something about the data. Now, it's not just a question of the size of the data, the amount of data, it's a question of the varied sources in the oil industry. And it's this that I found so fascinating. So I spent something like 18 years working for Schlumberger, and over that time I was able to learn about the different aspects of their business, partly because I worked in software in a group of mathematicians who actually were paid reasonably well. In Abingdon, near Oxford, it was a software house, and we were writing the software to build geological models and fluid flow simulators for reservoir engineers to work out the best places to drill wells. Now, the seismic data is, well, you make a loud bang on the surface, and then something like 1/millionth of the energy comes back in an echo, and from that you have to unscramble what the structure of the geometric structure and topological structure of the rocks is. If you have a well, sometimes they core the well, that is, they extract rock from the hollow drill bit all the way down the well. And that gives you very valuable information about what the rocks actually are. And now, they don't always core the wells, and even if they do, they put down what's called a well log, and that's, for example, Schlumberger, it's their core business, the wireline. Just about, if you can imagine a measurement, it gets made down the hole, except that you've got to compress the instrument down to something that's a few centimetres across. So things like nuclear magnetic resonance used in medical imaging, instead of you going inside it, they put this down inside the well, and from that you can extract information about the water and the oil content. Another important source of information are analogues, that is cliff faces, mines, cuttings and so on, where you can see what the structure of the rocks is. So once you see the cores, you know what kind of environment you've got. Is it a desert? Is it a sea or something? And then you can go and study the actual detailed structure. You know it's not going to be the same as your reservoir, but you can get a good idea as to the structure. And it goes on. So you do formation tests. Once you've drilled a well, you might pump the well up and then let it drop off. That's the same as a well test. You do the similar thing. And then once you start developing, you've actually got some oil, some gas coming up, and that gives you information coming up the well of the flow rates at different parts of the rock, because you might instrument the well all the way down and know what the flow rate is at different parts. So all of this is different kinds of data involving different types of physics, different types of chemistry. And what we want to do is to use this data to infer what the structure is in the reservoir so that we can then work out what is the best plan for the future development of the field to maximise, well, essentially maximise the profit. Now, so this is now very schematic. So imagine that we have a reservoir. They can be from, say, 10 kilometres, the biggest reservoir in the world, several hundred kilometres across. Typically, you drill hundreds of wells over a lifetime of the field, which will be a quarter of a century. But there are fields like Al Ghawr in Saudi Arabia, which have got thousands of wells, and they're talking about lifetimes of 350 years. Now, over that time, you don't actually know the geometry of the reservoir that well. It's several kilometres through the rock. You don't know what the properties are very well. And you don't know what measurements you should make. The measurements are expensive. So one of the difficult decision problems, which is becoming more interesting now, more feasible to study, is how to optimize the data that you gather. How do you control your uncertainty? And then you make decisions about where to drill, what flow rates, how much control you should to put on it. And the pattern of the wells you need to pre-calculate. And that's the problem. Now, in order to do this, we use a thing called, well, we solve a stochastic control problem. So what we have to do is to go through a workflow, which I'm going to describe in a moment. Before I do that, I want to explain what I mean by a feedback control policy. So this is a little bit of a tutorial in a concept that's particularly important and perhaps not as widely known. I found it very exciting when I first heard of it. So the example I'm going to give is, because it's a simple example to explain, is what we might call the markdown problem in supermarket management. So this is a project I'm doing in collaboration with Dunnhumby, and the student is Ozzy Rizith. And so this is a schematic description of what we're doing rather than a detailed actual. But we will be submitting a paper if there's a transactions journal coming associated with this particular meeting. So this is all written up. Now, the idea is this, is that you've got a certain stock. It could be some packaged food, and it has a sell-by on it. And you may have got a couple of weeks left on the shelves, and if you don't get rid of it in that time, you've got to dispose of it, which is expensive. So you want to gradually reduce the price to try and maximise your profit. Now, if you sell it all at the high price, obviously you don't sell very much. If you reduce the price too much, you lose money. Now, there will be a maximum price because you can't charge more than you actually put it out on the shelves at the beginning. And what we want to do is to calculate what price we should sell the stock at given a particular stock. So this would be, for example, at the early time, we have a particular stock marked by the arrow there, and then we go up, we've got a curve, and that curve tells us what price to charge given that stock, and that will be our decision. So what we have here is a decision rule, the rule being a function here, a set of values of prices given stocks, and then if we see what stock we've got, we know what price to charge. So we solve a problem, which I'm going to describe how we do that in a moment, but at the next time, say after a week, we decide to after a day, we decide to reduce the price, we have a new curve, which we have to calculate. We have to find that policy, the policy being the price as a function of the stock. Now, what's important here is that we have decided the policy in advance, that is, what price as a function of stock, but we haven't made the decision in advance because we don't know how much we're going to sell when we get to by the time we get to the next time step. And that's the important concept. You don't have to make the decision at the beginning. And that's important in all companies. So it's called real options thinking sometimes, where you actually delay as long as you can. In other words, procrastination is a good thing. But you have to do it optimally. And so it carries on. The next time you reduce your price again and you know what your policy is. So the question is, how do you go about calculating a policy? So you could call this computational policy making. This word policy is something that comes from control engineering. Statisticians call it a decision rule sometimes. And in general sort of everyday language, you might just say a rule of thumb. So this is the process whereby we compute an optimal policy. Now, the first part of it is traditional mathematical modelling. And in fact, that is perhaps in some ways the hardest part and the bit that mathematicians make a big contribution to. But they have to work with all the other experts from the other domains. And the first part in modelling is to decide what it is that you're trying to describe in the system, velocities, temperatures, or whatever it might be. That's the properties, which is what's important. And then you build a model. I'm not going to say anything here about how you might do that. There's some remarks in the paper associated with this, but that's something which perhaps we're more familiar with. Now, the other thing is at the beginning you might gather some data, because in general you've got to decide what data to gather. But I don't have time to talk too much about that. It's mentioned in the paper. Now, the key thing that I want to focus on here is the bit that these days we call uncertainty quantification. And then the previous speaker, Mark, did make the remark, which I happen to fully agree with, that uncertainty quantification is essentially a rebranding of statistics. And so is machine learning. It's a very similar set of concepts, different emphases perhaps in different areas. But the basic idea is, and this is a really important, the other key theme of my talk here, is you are uncertain. You hardly know anything for certainty. That's very rare. So you must be honest about your uncertainty. And to do that, we build a probability density that describes how uncertain we are. In other words, if you're uncertain, it's got a large variance. And it's important not to artificially reduce the variance. That's what we call being dogmatic. Now, once you've built a probability density, you can use the model, using Monte Carlo, to make a forecast, but a probabilistic forecast. Many, many different scenarios that pan out in the future. Now, a key thing, and the weather forecasters hold the moral high ground here, is that every time you make a forecast, before you actually do anything with the forecast, or simultaneously with doing something with the forecast, you should score the forecast. Because once you've got some data, you can see how good that forecast was. And you can learn a lot from that about how good your model is, how good your prior estimates of probabilities were. I should add here, I'm talking about probabilities in a subjective Bayesian sense. And I'm taking it for granted that that's a kind of point of view that people would accept. But I've given some arguments for that in the paper. Now, once you've tested the forecasts, you then assimilate the data to change your probabilities. And if you're lucky, your data is relevant and your uncertainty will reduce. That's not always the case. Uncertainty can go up because of the dynamics in the system. So in weather forecasting, your uncertainty could increase as you go forward. Sorry, I didn't get that right. If you make a measurement, you assimilate the data, your uncertainty is likely to go down. But that doesn't mean to say that your next forecast, the uncertainty will go down. It may be a chaotic system. Now, the key thing then is an important principle is that once you have to make a decision, and when you do that, the key thing is to make a very long list of your possible options. This is something that's often overlooked. And so one of the references in my paper is to Dennis Lindley's book on making decisions, and this is his key piece of advice. Don't make a decision until you've thought through what the other things you could do, what other things could you do with your resources. And then we calculate this policy function that minimizes our total cost, but our expected cost, because we take a sequence of forecasts going forward in time, and we worry about what will be optimal on average over those forecasts to take into account the upsides and downsides of different scenarios that may occur in the future. This is where the advice could be of general significance to people who try and make decisions rather than produce policies and don't factor in the uncertainty. And this, to me, is the industrial mathematics workflow. So just to summarize, it's modeling, forecasting, using data, testing the forecasts, and then choosing options, listing options, and then choosing the best one. Now, that requires a huge range of different disciplines, and that's where the collaboration comes in, and Poul is going to talk about that in a minute. So I should say a little bit about probabilistic forecasting. Now, I thought, being that he had the word mathematics in the session, I would actually write an equation up. The referees to my paper said it would be much easier to read if there was more mathematics in it, and I didn't really know whether I should follow that advice, but I have here. So normally a model, it might start off as differential equations, but it usually, in industrial mathematics, ends up as a computer program. And so computers are inherently discrete in time, and we use numerical methods in time, so we usually have some variables at time n that are updated from time n minus 1. There's some parameters, I call them phi here, which are the physical properties, permeabilities, conductivities, that kind of thing, and maybe some kind of stochastic noise in the system. And then we solve these equations, that's our model. Now, the thing is that we're not sure about the starting conditions, we're not sure about random disturbances, we're not sure actually what the equations are sometimes, so we might parameterize them, we're not exactly sure which wave equation to use, so we take that into account. And then we can make a variety of forecasts. And the key point I want to make, I can just relate this to our early experiences in the North Sea when North Sea oil was coming on in the late 70s, is that the forecasts were very optimistic. And people thought they were going to get a lot more oil out of the reservoir in a short time than they actually did. What happened was they pumped water down the injection wells, and then instead of oil coming up the production wells, you get more water than you thought because it breaks through. And the reason for that is that they weren't using proper probabilistic forecasting in the early days. What they were doing was taking a mean forecast. They would take the average properties and put those in the equations in an attempt to get the average behavior out. But it doesn't work like that. If you want to get the average behavior out and you want to work out your average cost, you need to use the full detailed randomness in each of the forecasts. So and you see this in a lot of economic forecasting and other projections, is people actually take an average and do a very smooth forecast. It's about the worst thing you can do. That's why forecasting has such a bad reputation. If you do it probabilistically, you really cover yourself. You've got a wide range, but then there's a very interesting thing about how you score the forecast, but that's another story. So let me just take a couple of minutes before I finish. I think I've got about 1 minute left. In practice, when we actually compute a policy, we don't actually compute the functions. We just need a computer program that can calculate the value of that policy function when we come to observe the thing, and our policies are then functions of our observations. So what we do is we actually do something that's heuristic and approximate. We use Bayesian statistics to estimate the current state of the system, data assimilation or uncertainty quantification, and then we actually do compute a sequence of actual values of decisions over the future that minimize our expected cost. But when we've done that, we only use the first decision in the sequence and we implement it. And then when we get to the next time step, the next day or whatever the time step happens to be, we then repeat the whole thing. We assimilate the new data and then we compute a new sequence of decisions. And in this way, it's equivalent to finding a control policy. And although it's heuristic, when we can actually solve problems exactly, we find that this heuristic technique, which is often called model predictive control, or open loop feedback control are the buzzwords from the engineers, it's surprisingly good. And that's actually that's the state of the art computing feedback control policies in things like oil production, price management, and so on. So just to conclude, in complicated situations, the mathematical style of thinking is essential in trying to manage the complexity of a system because it goes beyond what we can do intuitively. We have to acknowledge uncertainty. It's the key to good forecasting. We don't need to make decisions in advance, but we can choose our feedback control policy or our method of computing in advance. And finally, the complexity of all this involves us in the tradition of collaboration. So thank you very much.
So we'll take questions at the end of both talks, if that's okay.
Can you hear me in the back? I'm so happy and pleased to be here. And of course, I wouldn't be here without the help from and collaboration with a number of people. Should I change slides here with this? Yes. So a number of brilliant people, both here in the UK, in Central Europe, and in Denmark. So the topic is an enormous topic, industrial mathematics in Europe, and Europe is a large geographical region which includes the UK, as you can see here in this picture, and it's a subject far too vast to cover in 15 minutes, so I will try to focus on two things. Namely, I will describe an organization called the European Consortium for Mathematics in Industry, also known as ECMI. And I will briefly talk about some fairly recent new directions for mathematics in industry collaborations. So, ECMI, I love the word consortium. Like so many other things originated here in the UK with these study groups with industry that was begun in the late 1960s by these two Oxford mathematicians. And it became a regular occurrence in the 1970s, and the meetings began to be attended also by continental applied mathematicians and industrial mathematicians. And in some time in the 1980s, there was a consensus that there should be a European, again including the UK, organization to simply share standards for education, to also define what we meant by industrial mathematics, and as all these shared things have a network and collaboration where you share experiences. So if there are two keywords that you can take away from this, I would say that would be collaboration and education also. If someone had said in the 1980s we need a mission statement, they would have been immediately understood. And indeed, here's a mission statement. As you can see, education is big. We need to educate future generations of industrial mathematicians, and of course also to support all manner of mathematical modeling, because even then it was seen as what has come to be known as a key enabling technology. And finally, to do all this on a European scale. If someone had said in the mid-1980s, we also need a web page, that person would not have been understood very well. But see, here are the few centers from humble beginnings. We are now have a large number of member sites and ECME teaching center, and we also have a web page. And on the banner of the web page, you see the symbols and the equations of mathematics. You see the cogwheels of industry, and you see the graph, the network idea of a community. And on the black banner, you see a number of fronts where ECME is active, and I will briefly try and sketch a few of these. So, for one thing, there's the educational activities, which is big. So ECME has defined a standard or a model curriculum in industrial mathematics. Actually, there are several, because there are optional paths. You don't need to be an expert in continuous mathematics at the same time as you are with big data, or but there are these standard model curriculums, and if a university can offer with English instruction these models, it can apply for and become an official teaching center for ECME. And if a student graduates with a master's degree from an official teaching center, they will receive a certificate for being a master. Now, the certificate is just a piece of paper, and I'm sure students find it useful to add to their CVs. But the whole exercise of defining standard curricula has turned out to be very, very useful, especially for some emerging universities that want to have a clear description of what it means to be able to say, we educate industrial mathematicians. Another wonderful activity under education are the annual modeling camps that have been going on for nearly as long as ECME has existed. Every summer, students, also UK students, gather and address industrial problems under the supervision of an ECME instructor. And the students, certainly the students I sent away to these things, come home starry-eyed and excited about having discovered that they know some stuff and they can collaborate with students from Finland to Portugal and discuss industrial mathematics and actually solve problems. And the ECME instructors come home, and this is not so common for teachers these days, actually have are positive about the future and have hope for future students. So they're really wonderful events. ECME does scientific conferences every other year. So last year it was in Santiago de Compostela in Spain, a very successful conference, and we have high hopes for next year in 2018. It's in Budapest. There's dissemination activities with journals, with books, with blogs connected to the web page, and we give out prizes for spectacular work and best theses, and so on. There's a thing called special interest group, where we actually support experts getting together around a highly specialized subject, and we fund we seed activity so that they can meet each other and do early work and maybe submit joint proposal within a special area of industrial mathematics. And this has also been a good activity. Finally, something about new directions. I was just told by Jeff Everett that there's been some very good experiences with single-day study groups. Did I miss the study groups? I think I did. Yes, I did. I missed the study groups. I knew there was something bad here. I have to say something about the study groups because this is so close to my heart. Here's the famous picture that we have used many times in the Danish study groups because of this saying in Danish engineering: to build a bridge you need steel and mathematics. And as many people in the audience know, these are the week-long workshops where mathematicians solve industry changes. And I'm proud to say that the first study group outside the UK, not by many months, but we were actually the first in 1998 to have a study group in Denmark. And ECME back then was already enumerating these study groups, and the one we held back then was number 32, followed very quickly by the Dutch. A few weeks ago, they had a study group, European study group with industry, number 128 in Ireland. And in August, we will have in Denmark number 129. And in early September, here in the UK, number 130 will be held in Warwick. So these study groups have multiplied and spread all across the continent, and they would only do so simply because it is a fantastic catalyst for industry and academia interaction. Okay, now on to the new directions. And I mentioned the one-day study groups in Manchester. So not only are they one day, they are also single company study groups. This is an interesting new format. I hear also that in Holland they have tried single morning meetings. Now these are not study groups, but they are simply breakfast meetings where industry comes and have informal discussions. So you could call them sort of seed activities for upcoming study groups, but they have been successful. In Poland, Kamil Kolaszka is heading the Center for Industrial Applications of Mathematics and Systems Engineering out of the Polish Academy of Sciences, and this has been extremely successful. And a fourth format I would like to mention is the flying squad or rapid response team that we have experimented with in Denmark for companies that have a sudden need for a problem and hate to wait maybe 3/4 of a year for the next Danish study group, and for some reason may not want to go to a study group in a different country. We can form a small team and have a 1 or 2 day visit with the company and see if we can solve their problem. There are new networking efforts, so you can see collaboration and networking is a big theme, and all these activities, including ECME, have a graph structure in their logo, So does EU Mathing, and Will Schilder's sitting here formed this network of networks where rapid information exchange and knowledge transfer between the key players is the central focus. And finally, funded by the EU, MINET, a so-called cost action, actually has real money to support the creation of first-time study groups in places where they might not have formed otherwise, or short research exchange of industrial math researchers. So this is a very quick run through. So in conclusion, I hope to have convinced you that there's such a thing as the European Consortium for Mathematics in Industry. From humble beginnings, it has grown now to be a solid and big organization in Europe. And one of the successes has been to set these educational standards, but there are other things like the study groups with industry that we are overseeing, the modeling weeks for students, the dissemination efforts, and then in addition to ECME, we see in many places in Europe, and far too many for me to cover here, centers, activities. There's very much excitement about mathematics in industry. And now we must hurry. No, I think it speaks for itself. Okay. We have to hurry.
Fine, we'll bring both of the speakers back up on stage. So perfect timing, guys, so we have a few minutes for questions. So again, I open up the floor up for questions. Julian.
So, wearing exactly my sort of parliamentary hat. We've had lots of discussions in the UK about the question of Europe, and one of the issues was actually made by somebody from the European Commission when they were here. That already, of course, the EC runs networks or sponsors networks which extend outside the existing EC. For example, Israel, North Africa, of course, Norway, and so on. And I think one of the things that ECME presumably will get support from the European Commission for networking, but the only point is for the Brits, they will not get money from the European European Commission, but they will, as it were, be able to participate in these networks afterwards. I wonder whether you'd like to comment.
Yes, so my comment is that ECMI has never received a penny from the European Union. We are completely separate as an organization. It's a grassroots organization, and so we are not entangled with the European Union at all. So of these efforts that I mentioned, only the last one, MINET, is actually sponsored by the EU. But ECMI has never been, and we are really so we fund ourselves by membership fees. So there's no entanglement
but
with the EU.
But this new activity sponsored by the
yeah.
by EC will become progressively important in other networks. For example, Flow and turbulence. There is funding into various projects there from Brussels.
Yes.
And this requires some diplomacy to make sure this works effectively.
On that, I completely agree. A number of a big element of diplomacy will be required, and some thinking about that. Because for sure, the EU is supporting or is looking favorably at mathematics in industry, as and will give money to mathematics in industry. And so we'll have to see.
Any other questions? Richard, back.
Thank you. I wanted to just comment that industry is part of the modern economy, which is the title of this meeting, but not the whole of it. Do you see any special differences or difficulties in having comparable study groups with, for example, third sector organizations, government organizations, and other things which are not conventional for-profit industrial companies?
Are you thinking about single company study groups or study groups with organizations which are maybe not classified as industrial organizations?
I mean that not every player in the economy is a traditional company, and not every part of the economy is industry, and yet all parts of the economy are covered by the title of this meeting, and all parts of the economy can benefit from the input of mathematics.
Industry is much broader than...
Much broader than that, yeah.
As you define, what was your definition of industry, social or economic value?
Of all social and economic value, and we mean that seriously. So it does not have to be a private company in that.
But Richard, I think, was thinking about the study groups in particular, and do we include policymakers bringing problems?
Well, we've had police coming to study groups.
Yeah.
We've had economists asking about
Very much
questions. So anything that's amenable to any kind of quantitative description involving some kind of data, I think is amenable to a study group.
Yes.
As long as everyone's open-minded.
Nuclear arms verification, for example.
Any other questions, John? There's a microphone coming.
About a year or so ago, they started one comparable organization in Asia Pacific. I don't know if you know about that. The Asia Pacific Consortium for Maths and Industry. I wonder whether ECME should be trying to collaborate with the people where everything is changing much faster, and possibly helping them and getting some benefit as well.
Definitely. I would need a bigger map, but apart from that, the ideas are surprisingly and wonderfully the same, and the challenges are the same. So you're right, we should.
Rather than reacting to the industry, do you actually go out and say to companies, you can solve this better this way, and just give me £10,000 or whatever?
I wish we had the resources to knock on doors in the way you are. But so we are just hoping that our dissemination effort reaches as many potential, you could call them clients or collaborators as necessary. But we really don't have the means to do that. When that's said, I will say that so my experience with organizing study groups is I often follow my own students after they've left the university and gotten their first jobs, and I visit them in their first jobs, and I talk to the company, and more often than not, the company then realizes that they have something that could have a mathematical solution. So that is done to some extent.
I think we're in danger of cutting our afternoon break, so I think probably we should finish there. So could we thank our speakers and all of them in the session today? Thank you very much.